And we'll go to this first slide. There, you should be looking at the hydrological cycle. Has everybody got that? I'm going to presume that you are. This is a nice picture, and everybody is usually familiar with the hydrological cycle. So I'm not going to go into it in detail, but what I'm going to ask you now as participants to do a little controlled visualization. I want you to relax, sit back, take a couple of deep yoga breaths. In fact, you can even go into the lotus pose if you want. And picture yourself on the top of a high granite peak. And you're looking down at the valley below. And what you're seeing through the mist and the rain is a little bowl-shaped valley down below this mountain peak. The rain is falling all around you and onto this granite peak, and I want you to float off the top of the mountain and slowly follow the track that the water is forming, these little rivulets running across the face of the granite as they go down the side of the mountain, heading for that little lake. And as the waters approach the lake, they run in the cracks in the granite, they run into the rubble that's fallen off the granite, they run into the scree slopes, and they end up in this little lake. Now this is a bowl-shaped valley which geologists call a cirque. And this little lake, they've got another name for that because they're so important, is a tarn, T-A-R-N. And these little lakes, these tarns, are all over the Columbia Basin, all over the mountainous regions of the world, actually, wherever there has been glaciation. And if we float ourselves off to the left here and look back at this tarn, we'll see that this is actually the head of a valley, and it's a hanging valley. You can see from the shadow of the trees that this Clearwater Lake is actually high above the main valley. So since we're visualizing, let's visualize a waterfall coming off of that, over that cliff and falling down below. And since not much water is coming over, it's going to be a nice wispy, white, mare's tail type of waterfall falling to the rocks below and gathering together into a small stream. Now we're in the main valley, so that small stream is going to wander down the valley. And it's going to pick up little side streams. And remember, it's raining, and the rain is falling on the trees. And as it falls on the trees, it drops to the duff below and down through the duff into the mineral soil. And it comes out as little seeps as well as coming into other streams. And the stream keeps gathering size as we go down the valley until we come to a little flat spot. And this little flat spot was created by the glacier that flowed through here 15,000 years ago. And in that little depression that was left by the glacier, we have a wetland. A wetland, as you know, is filled with all kinds of interesting and strange things. And there'll be pink spirea, people call them hardhack. There'll be grasses, and there'll be sedges. There'll be willows along the edge. There'll be some other small trees. There'll be yellow birds. There'll be dark birds. There'll be blue dragonflies. There'll be toads and frogs. All of these things that live in a wetland and make it such a complex place. And the water that's in this wetland, which we've been following down the creek, is now subject to the forces within the wetland. And one of those forces is for the plants to take nutrients out of the water so that they have it to grow with. And besides the nitrate and the phosphate that they might take out, they're also going to take out heavy metals. And so the heavy metals get trapped in an endless cycle in this wetland. They live in the body of the vegetation, and when some of the vegetation dies, they're released and immediately taken up by other vegetation. So a lot of the heavy metals that are in the water are actually trapped in this wetland. At the north end of that wetland, that's the direction we're looking, the water escapes out of the wetland and continues down and leaves this beautiful wetland with all of these grasses and everything else, and continues its travel down the valley. About 1 kilometer south of that, or no, pardon me, north of that wetland, there's a junction where another valley comes in from the right-hand side. And the two streams coalesce at that point and turn and run west. And they run along a division, a separation in the geology. On all of the rocks on the left-hand side of this valley are granite. They're part of the Nelson batholith, and so there's not very much soluble material in them. On the right-hand side, leading up towards Idaho Peak, we have metamorphic rocks. These are rocks that were deposited as sands and shales, became hardened into sandstones and shales from the clays that were deposited, and then under pressure and heat became metamorphic rocks and turned into quartzite and slate. And so depending on the degree of metamorphism, those rocks somehow have a little bit of permeability in them. Sometimes they let water in. They're much more susceptible to having things dissolve out of them and flow back down through the little side creeks and through the soil to join this creek as it flows down. And this valley ends at a notch. It's a notch in the bedrock, and the creek water flows out and flows, in this case, it flows across a little delta of gravel and joins the waters in Slocan Lake. And we're going to stop our visualization for a second as far as the flying goes, and we're going to walk down, climb down to this creek, and we're going to fill a couple water bottles with water from this clean, clear mountain stream. And then we're going to take those water bottles home with us. You'll see the picture of the two water bottles there. And we're going to pour out of the 1 liter bottle, we're going to pour that into a Pyrex dish, put it on the stove, and heat it up. And we're going to boil all of the water off until there's nothing left but a little bit of brown, tan, buff, whatever the off color is, just off white sludge that's in the bottom, because ions don't evaporate. Only the water evaporates, and it leaves these solids in that Pyrex dish. Now, if you want to know what they look like, look inside your tea kettle when this session is over, and you'll see it has a scale in it. That is total dissolved solids. Those solids were in the clear water. They were completely dissolved, and they were completely ionized. So total dissolved solids, or for shortcut we'll call them TDS, is the weight of those solids that were in 1 liter. So we dumped a liter of water in that vessel, we boiled it, and then we weighed the vessel, and if we know the weight of the vessel before we had boiled off the water, we subtract the two and we get the milligrams, and it will be milligrams because it's very fresh water that we're dealing with in these mountain streams. It'll be in milligrams per liter. And some people will call TDS parts per million. In fact, when we look at the handout that you have, we will actually look at a correction that I need to make on that. Some people will refer to them as parts per million. Parts per million is weight per weight, and what we just measured by boiling off the water was weight per volume, we had a liter of water. Now, most people know that a liter of water weighs a kilogram. And a kilogram is 1,000 grams or 1,000,000 milligrams. So why isn't milligrams per liter the same thing as parts per million? And the answer is that a liter of water that has things dissolved in it, think of putting salt in water and it gets dissolved, you actually increase the density of that solution. So milligrams per liter versus parts per million can be changed back and forth between them by using relative density. And on the screen in front of you is two calculations. And look at the second calculation. Seawater has about 35,000 milligrams per liter, mostly sodium chloride in it. And if you divide that by the density of seawater, which is about 1.025 times as heavy as regular water, you'll see that the parts per million is a slightly smaller number. And the larger the milligrams per liter is, the greater the difference between the parts per million. All of that's interesting to us engineers, but to the average person, just whenever you see parts per million on these fresh waters, think milligrams per liter, because all of the analyses are done in milligrams per liter. But this is important when it comes to thinking about percent, because everybody knows percent is parts per 100. So when you look at the seawater calculation, where I had 34,146 parts per million, and if I cross off 4 zeros of the million and move the decimal place 4 places over on the other one, you'll see that seawater is about 3.4% solids. So that's what would happen if you evaporated seawater. So let's get a feel for what total dissolved solids look like. Total dissolved solids of distilled water are 0. That's the steam that comes off your tea kettle. And if you condense it, it has no solids in it, because as I said before, they don't evaporate. The tarns, those little lakes up in the tops of mountains, they're up about 2,000 plus feet. They're usually less than 50 and usually quite a bit fresher than that. Mountain streams in this area throughout the Kootenays run about usually less than 100, sometimes a little bit more. In some cases you can get them up to 500 if there's a lot of soluble material around, a lot of mineralization or a lot of limestone. So in the East Kootenay, where the streams are coming out of the Rocky Mountains, you're going to see these higher numbers. Anytime they've got something over 1,000 milligrams per liter, look for contamination in it. And we'll talk more about how we use total dissolved solids in interpreting water analyses. But for now, recognize that seawater is 35,000, and the saltier you get, you can actually get up to 300,000 milligrams per liter. That's 300 grams of soluble salts in them, in water. That would be a very, very salty brine, or take a glass and put a couple tablespoons of water, a couple of tablespoons of your table salt in it and stir it up, and that would be 300,000 would be the amount that it could dissolve of the table salt. So the example that we're going to look at is a Caro analysis from Mirror Lake, and I'm going to use it to illustrate what waters look like in this area. Mirror Lake is just south of Kaslo, and this sample, I don't know exactly where it got, but I'll show you how, and I don't know exactly where it was caught, but I'll show you how I've interpreted it to know a little bit about the source of the water that is there, simply by interpreting it later on in this talk. So what you see there is 2 sample bottles, which I've gotten from Caro Labs in Kelowna. And the big one is a 1 liter sample bottle. The little one is a 250 milliliter sample bottle. And it's unique in that you ask for a preserved sample bottle because you want to look for the metals in here. And the metals are the bad ones that cause sicknesses and, for instance, lead or mercury, arsenic, things like that. And to catch those samples correctly, you really have to have a little bit of nitric acid to drive the pH way down. So Caro will give you a preserved sample bottle, and you don't rinse it out. You just fill it with 250 milliliters of your water that you want to send to the lab. And then you put it in a box that's got a cooling system in it, or a ice pack, and you send these samples into Caro Labs, or whatever lab that is your favorite lab. And they take a little bit of time and some of your money, and they come back with a water analysis. Now, I hope that Tara sent these out to you, but here's what the results will look like when they come back. There's 2 parts to this. The first is from the Interior Health, and Interior Health actually did some coliform work on this.
Richard,
now,
can I interrupt you for a sec?
You bet.
Sorry. I didn't send that handout prior to the webinar of the water analysis, and I just you can access it. I just uploaded it to the webinar, so you can actually access it in that little vertical toolbar down. There's a section that says handouts, and if you make that go to a minus sign, you can grab that and just open up that file. It's actually 5 pages long, and he's got the first 2 pages there. You can see why we wanted you to have them, to access them. Anyway, so I just wanted to let everybody know where that was. So back to you, Richard.
Okay, then. Okay, thanks, Tara. It's not important that you have them downloaded. You can leave the download until later, and then you can puzzle over them, and because what I'm going to do is go through it a little piece at a time and explain what all is happening with that analysis. So it will come in 5 pages when you do download it, and the first page will be the one that you see on the left of this screen, which is the one from Interior Health Authority. And I'm going to answer a question here that has been already asked, but I know about. This one is looking at coliform. And coliform is a specific type of bacteria that causes all kinds of bad things to happen if you ingest it. And the Interior Health people are very interested in knowing whether we're having coliform growths or coliform is being lost into our water systems, because the coliform comes from human or animal feces that carry it. So it's a bacteria that is actually inside your stomach or your intestines in any case, but you don't want to be eating it and drinking it. So coliform is an important thing to do, to take, and it's taken in a specific manner. The samples of water that are used for coliform are caught in clean. They actually have a fancy bag that you can catch them in. You can't rub your fingers inside the bag or anything else. The bag is immediately put into the dark and shipped by a chilled container of some sort to the nearest lab. And in this area, Passmore Labs does coliform counts. And within 24 hours, they have to have that in their lab, and they make cultures of it and do coliform counts. So that's a little bit different than I usually talk about on water analysis. I usually concentrate more on the chemical aspects of it, but there's the results on coliform. Now on the right-hand side, you'll see certificate of analysis. Then the next 2 pages in the handout, or which you will download eventually, is actually about the sample data. So the next 2 pages, I will be going through those as well. And the final page doesn't have anything of significance on it, so I haven't even made a copy of it. It didn't have anything to talk about. So let's take a look at page 2 of that analysis that we were looking at. We've moved off the coliform page, and now we're onto the actual chemical page. And you see the box that I have down at the bottom outlined in red. Let's take a closer look at that. And here is what Caro Lab says on this particular analysis, what the units are. And I've underlined already milligrams per liter, second line down in that little table. I've underlined equivalent to parts per million. And on these fresh waters, they are, because the density of these waters is basically 1. So it's important to differentiate if you're dealing with brines, but if you're dealing with these fresh waters, you can just assume milligrams per liter, parts per million mean the same thing. It's within the accuracy of the lab, actually. And then they've got micrograms per liter, and they say that's parts per billion, which is the beautiful thing about the metric system. You just add and subtract zeros whenever you like. The headings on the column that we're going to look at next, they're going to have a few things in the next 2 pages. One of them is the detection limit. RDL will be the heading at the column. Less than, we all know what that means. AO is the aesthetic objective, and MAC is the maximum acceptable concentration provided by various agencies that are concerned with these things, and they've laid out these guidelines. So let's take a look at page 2, the top of page 2, and it looks like this. It's got on the right-hand side when the sample was prepared and when it was analyzed. I've drawn a black line vertically between RDL and the units because the two, even though they look like they're together, there is a separation. The RDL is the actual milligrams per liter, for instance, that the alkalinity can be detected at. So looking at that red box, now I'm going to blow that red box up because that's the only thing that I want to talk about at this point, is these are the general parameters of the water analysis. And you'll see that I've outlined or underlined 3 of them in red: the alkalinity, the chloride, and the sulfate. And when we're looking at a water analysis and looking at those total dissolved solids, 95% of the weight that we measured when we boiled the water off, when we measured that, 95% or thereabouts, even higher on some fresh waters, is composed of 8 different ions. And I'll talk more about those later, but 3 of those ions, or pardon me, 4 of those ions are anions. They're negatively charged. They're chloride, bicarbonate, sulfate, and carbonate. And alkalinity is a measure of the carbonate and bicarbonate content. Now you'll see at the bottom I've written the bicarbonate concentration is 1.22 times the alkalinity for a pH between 8.3 and 4.5. Now that's a kind of an obscure and roundabout way to get at bicarbonate and carbonate, but this is the way the labs do it, so this is what we work with. And alkalinity is shown there as total calcium carbonate, but the bicarbonate ion itself is actually 1.22 times that, and I won't go into the fancy math that allows you to do that. So I have on this page 3 of my 4 anions: chloride, sulfate, bicarbonate, and now the magic comes in because this pH, which is the other blue box that you have there, is actually below 8.3. So let's take a look at how carbonate and bicarbonate and pH are related. So on the right-hand side, you see some nice pH meters. But if you look at this picture, what you'll see is on the left-hand side, the pH scale, which runs from 0 to 14. And along the bottom, I just have acid volume. And if you take a look at the blue line that has a couple bends in it, that is a titration curve taking a sample of watery fluid with a pH of, say, 10.2 by the look of it, and start adding acid to it. And you've all probably done this at some time or other in a chemistry lab, where you drop little bits of acid and keep recording the volume that you used. And that curve has a bend in it, a little inflection point, at a pH of 8.3. And if you keep on adding acid to it, then you'll get another inflection point at a pH of 4.5. Those are those two red lines. Now those are magic lines. The top one, 8.3, is where phenolphthalein turns color, and the bottom one is where methyl orange turns color. So you can do this without a pH meter. You can just use those as indicators. But I'd like to direct your attention to the flagpole on the right-hand side and take a look at those flags that are sitting there. The second flag down says bicarbonate, HCO3, and carbonate only exist between, together, pH 8.3 and 11. That's the only place you have carbonate and bicarbonate in the same sample. You go down to the third flag down, which is about the middle. In between 8.3 and 4.5, you only have bicarbonate. And that's why I was able to take that alkalinity and say that alkalinity is all caused by bicarbonate. Now, if you go down the page, this is still on page 2, there's another little frame of data. And this one is called hardness. It's called calculated parameters. And the one I want to direct your attention to is the hardness. Hardness used to be measured. You take a bar of soap and go to the water and rub your hands in the soap and try and make a froth. And if there's calcium and magnesium in there, you don't get bubbles out of your soap. And ion balance we'll also come back to, and total dissolved solids we'll also come back to it from a different angle. But that's just to let you know what those boxes are about. And I'm not going to bore you with the details of how you do the math, because it's all laid out there. And this whole presentation that I'm doing, this PowerPoint presentation, will be made available to you after the seminar is over or the webinar is over. So I will either ask you to email me or Tara and ask for it if you want to play around with these calculations. Now we come to the interesting thing. This is still on page 2 of that. This is on page 3 of that report. What you're looking at here is the same headings as we had previously, but now we're going to look at the positive side of the ion, because all of these total dissolved solids are in the form of ions. We're not talking about any sediment here. So if you look at the Mirror Lake sample there, you'll see there's a whole bunch of data on the positives, and this contains good and bad things. Bad things being heavy metals, and good things being things that you need in your life. Calcium is necessary in your body, as is magnesium and sodium. This is the 4th page, and it's just a continuation of that same table. Now, to make things easier, I turned around and put that whole table onto a spreadsheet so that I can play around with it. So on the left-hand side, the first column is all of the different things that have been analyzed by the lab. And the lab analyzes all of these by sticking it in a fancy thing called an ion-coupled plasma or an atomic absorption machine, and they measure all of these things. But they only have a certain lower limit to which they can get to on specific ones. So that's the column headed Caro Lab detection limit, and that is on their report. And it shows that they can't get any lower than 0.005 milligrams per liter. After that, they just put less than. In the Mirror Lake case, I've outlined it in red because the answer is 0.163 milligrams per liter, which is above their detection limit. But if you look at the yellow column, there is the Caro's an definition of what is important from a drinking water standpoint. And if you look on the right-hand side, the definition of those different acronyms are laid out there. They say aluminum is an aesthetic objective. In other words, maybe it starts to taste or something. Antimony, you don't want over 0.006, and that is the maximum acceptable concentration, and that's a Canadian standard, as are most of those other MACs. If you look at the next one, 2 columns over, the source is listed on the right-hand side. It's an older listing of acceptable concentrations based on various agencies that have set those. But what I want to show you here is a couple things. One is aluminum is the only one that is above the aesthetic objective listed by Caro. According to the European Economic Community, you can have 0.2, so it's below that. The calcium is not important. It's green. It's one of the necessary ones. The magnesium is colored in green. It's another necessary one. Potassium is another one we need in our bodies, as is sodium. And remember I said there were 8 ions that we were concerned with, and we talked earlier about the anions, the negatively charged ions. But the calcium, magnesium, the potassium, and the sodium are the positive charged ones, and they will exactly offset the charges from the negative ones because water is never charged. So we're going to look a little bit more detail at this on the next slide. But before we go there, look at the pink color that I put on some of those. Those are the only ones that were above the detection limit from the lab. So I've colored in pink only the measured strengths, the milligrams per liter. Now this beautiful picture of this man collapsing in a pile of heavy metals I stole directly off the internet, and it shows some of the bad heavy metals that can cause us problems. I have no justification for saying that those are right or wrong, but I've put arrows on ones that I know that are important when we start talking about drinking water. Arsenic, we don't want drinking water with arsenic in it. Cadmium is a very bad one. Chromium is also very bad. Don't lick your chromium yellow oil paints. Lead and zinc, which are down at the bottom, are very common in this area where I live because we have lead zinc deposits here, sphalerite and galena. Mercury is always in the news with connection with fish, and nickel is in too much, along with copper, can be harmful to you as well. So I'm going to take a quick break here and see whether there's any questions up to that. That's pretty heavy stuff and a lot of information in a very short time. Tara, what have we got?
Well, there was a question. There's a couple of hands up, and I'll address those in a second. And if people still want to do those, I was trying to back channel, see if I could get them to type their questions in. But here we go. Susan had a question. Is total TDS, total dissolved solids, is that the same as total suspended solids?
No, not at all. Total suspended solids is a turbidity measurement, and it's the stuff that's floating around. And if you send a sample bottle to the lab that has suspended solids in it, they'll have settled out probably by the time they get there. They will run it through filter paper and filter those out. So suspended solids are actual particles of grit, clay, sand, and they'll get those out as much as they can with filter paper. So dissolved solids are completely ionized and completely dispersed in the water.
So now I'm going to try unmuting Jeff Delves. Hi, Jeff. We'll see if, do you have a question that you want to just get out loud?
I don't have a question, no.
Okay, I just noticed your hand was up, so I will mute you again, unless you know.
Okay. Oh, I don't know how I did that even, so.
Okay, that's cool. And then there was one other person that I'm going to just check in with. Oh, no, I can't. Oh, it was probably a connection issue because I can't actually get her. Okay, so there was Susan's other question about E. coli counts, but I think that you addressed that.
I hope I've covered it, but if she wants to talk more about it, we can do that after the next little bit. I have a few more minutes to go of showing what we're going to do with this, so what this information is used for. So if she wants to type in a little more detail or wants to go online after I've gone through the next part, I welcome that.
Okay, I think that's all the questions in the chats that I have here so far, so I think we can pass this back to you. How's that?
Okay, great. Okay, what you're looking at on the screen here is the introduction to the next part of the story about waters. What you're looking at here are supposed to actually be two conductivity meters. The one on the left definitely is a conductivity meter. It's the same type that we use with the cabin water monitoring that we're doing on Silverton Lake here with Slocan Lake Stewardship Society. The one on the right is a composite meter. It's got a temperature probe, it's got a pH meter, and it's got a conductivity meter all built in to the one, and you can carry it around in the field quite nicely in your shirt pocket. Conductivity is a measure of how easily the fluid conducts electricity. That's why it's called conductivity, conducts the electricity. And the ions, because they are charged, create that carrying capacity to take the charge from one of those plates across to the other, looking at that particular sketch. And the more of those ions that you have in the solution, the easier it is for electricity to flow through the solution. And the result is that you can use conductivity as a measure of the total dissolved solids. The metals, because they're quite a small part of the whole structure, really are not important in the conductivity measurement. More important is the number, the type of ions that you have and the number of ions. For instance, chloride ion is a nice little round ball floating around in there with a negative charge on it, and it bounces back and forth and carries charges back and forth between those conductivity plates quite easily. Carbonate, on the other hand, is only half as active because you've got one carbon atom with 4 oxygens clustered around it. So, pardon me, with three oxygens around it. So it doesn't conduct as much. So it's a measure only of the main ions. There's a natural annual cycle to that, and we're going to look at that in just a second. Any stream that is coming out of the mountains here has a change in total dissolved solids depending on what's happening meteorologically and those things that happen on an annual basis. And I'm going to show that to you in a minute as well. So what I'm talking about here is what you can do with the conductivity meter, because it is far cheaper to walk around with a conductivity meter and pH meter in your breast pocket and stick it in the water in these various places and record what's happening and pretend that that means total dissolved solids, because the lab will charge you anywhere up above $100 for that full-blown analysis we were looking at, not counting the coliform. The coliform is another $40 or $50. So the conductivity is a nice, easy way to start interpreting the quality of the water. So here is a nice little stream that is just outside of where I live here. The red lines actually are supposed to fall about between December and January. That's the start of the year and the end of the year. And what you'll see is the conductivity is fairly high in the winter when there's not much flow in the stream. But come May and June, when the streams start to flow high and hard because of the melting snow, the conductivity actually falls. And then again, when it slows down after that spring freshet, the conductivity goes back up again. And the interesting thing about that is it just goes the opposite way from the flow. In other words, the conductivity is high when the flow is low. And when the flow from a stream is low, the conductivity is high. And that has to do with that first little visualization we talked about. When you've got a heavy rainfall that soaks through and into the soil, it sometimes doesn't have time to actually reside in the soil and dissolve very much for long, because a lot of these ions are actually in the soil. They're not in the rock faces themselves, and they're not in the rubble or the scree slopes. Water runs through those fairly quickly. It has to do with the length of time it takes in the soil. So actually conductivity is a measure of the time and the length of the flow path that the water has gone through. Now here's a very interesting little one. Look at the size of the conductivity in the winter when there's hardly any stream flow in this one. This is a very small stream. It has a very short drainage, and the other bad news is there's a old mine site there with water flowing out of the entrance. So when there's a low stream flow, it's really coming out of the water, water coming out of the mine entrance a lot. And as soon as you get spring freshet, it just drops all to pieces there and goes down where now you're getting runoff water, not the seepage water. And then it climbs up again. And then you'll see, and this corresponds with the previous one, that there was a rain event, because both of these are not too far apart in the same rainfall area. That back in November, there was a heavy rainfall event. This was 2014, I think, yeah. And it dropped the conductivity. So this is a dramatic example of how conductivity varies with rain events and with snowmelt. Here's a dramatic example of what happens when a stream runs into the side of a parking lot at Sandon and washes away the fill that was used to make the parking lot. And there's all kinds of stuff coming down here besides the obvious clay and silt that's being washed out into the lake. This is Slocan Lake. The town site is New Denver, and that's Carpenter Creek coming down from Sandon. And you can just see the immense flow. In fact, if you look along the shore to the right, see the marina there. That marina mouth is plugged up so badly this year that you can hardly get the boats out. the stream is cleared up, but the silt and debris that came down has been moved along shore and is now filled in that entrance to that marina. Now, when we were doing a lot of the swamp work here, we've analyzed analyses from 25 different locations, some of them high, some of them low, as far as elevation goes. And so this particular picture is the result of correlating the total dissolved solids from all of those analyses with the conductivity, because we had full analyses on, I think it was 21 of those, and out of those you'll see that a couple of them were contaminated and had quite high conductivities, but all those little red squares are consistent, and they're consistent because all of the waters around here, the main ions that they have access to are calcium and bicarbonate. So these are calcium bicarbonate waters, and you can actually correlate, and I can look at a conductivity reading in any of these mountains around here that have calcium bicarbonate waters in them, and most of them, in fact just about all of them that I know of, East Kootenay, West Kootenay, all are calcium bicarbonate rich waters, and I can, using that graph or using that little equation that I have worked out there, I can tell what the total dissolved solids are. So let's take a look at that water analysis and look at it the way I look at it as a hydrologist and a geologist. I plotted the same data that we had on the analysis onto a little form that I've developed. It's a little Excel spreadsheet, and what I've put into the blue box that you see there is the sodium, potassium, calcium, and magnesium, the four main ions. You'll see I have a couple other ions shown up there, barium, strontium, and iron, but there's no significant value concentration of those. On the right-hand side, on the anion side, the negatively charged ions, I have chloride, and I have bicarbonate, which is the HCO3, sulfate, and carbonate, and I put those in a pink box. And those are the main ions that we have in that Mirror Lake water sample. So if you add up the milligrams per liter of sodium, the weight of the per volume, sodium, potassium, in other words, all the cations, and all the anions, and add the two together, you come up with the total dissolved solids that's calculated to be 99 milligrams per liter. And if you look at that little diagram, you'll see something interesting as well. These 8 ions are plotted in a strange manner. It's a semi-log plot, and it runs both ways from the center, and don't worry about that. It's what I'm doing is visualizing those ions to compare to other water analyses in the area, which I'll show you in a second. Now, you might question me as why I didn't put in some of these other ions. For all of those metals that we had there, we had a page full of metals. What happened to them? Well, here's what happened to them. If I add up all of the concentrations of all of those without adding in the green ones, which are the 4 that I've plotted, I'll come out with 2.8 milligrams per liter of the metals. In other words, my major ions make up 99 milligrams per liter. The concentration, the concentration of those metals is only 2.8. In other words, only 3% of that analysis is affected by the trace metals. So going back to those little diagrams that I had at the bottom of that page, I have 4 of them shown here. Now those diagrams were invented way back in 1950, in the mid-50s, by a water worker, a fellow that was really interested in doing work with freshwater systems, and his name was H.A. Stiff, and so these are called Stiff diagrams. Now if you look at the top one, that's a tarn that is in the watershed just above Pass Creek. There's a little lake up there. I think it's called Goose or Gander Lake. And you can drive up to it. It has a total dissolved solids, if you take a look at the top left-hand corner, of 18. Extremely fresh, just about rainwater. And all it has is a little bit of bicarbonate showing in it. If you come further down on that page, you'll see one that's labeled wetland. And look at the total dissolved solids, 49. And it has a little bit different shape. And this is what the stiff diagram does, is it allows me to visualize these waters. And then if I go down to the valley mouth there, which is a different wetland, different watershed again, but still falls within the calcium bicarbonate system, you'll see that it's 120. So I'm looking at this, and I can actually look at these pictures and say, hey, that really skinny one up there must be high elevation, correct? And it must be very fresh, and it is. The middle one, less fresh, but still extremely fresh. And the bottom one is more typical of the waters that you see down in the bottoms of the valleys. For instance, Columbia Lake is probably running about that. So those are three that were from different watersheds in the area here that we analyzed. Now I take the Mirror Lake analysis, which drains into the Kootenay Lake, and I see what my total dissolved solids there is 99, and I see it's a calcium bicarbonate water, and I can actually fit it into this whole pattern and say the Mirror Lake analysis, and correct me when I go wrong here, Tara, the Mirror Lake water is draining from a much larger system than that Little Tarn, definitely, and probably from this wetland. So let me jump to this last slide here and say, here is the visualization we did at the very start. Up here, let me grab a little pen here. Up here, that Little Tarn that we were looking at in the visualization, down in the bottom right-hand corner. We then went down the creek, and we came to the wetland, and then we came to the junction, and then we came to the creek mouth, which is off on the left-hand side. Fisher Maiden Lake, which is not a tarn, but is partway down, you'll see it has a total dissolved, a conductivity of 52, quite fresh. When we get down to the wetland that I talked about, the water in there, the conductivity of about 70. And following down, we see that after the junction, we jump from 69. Now we're picking up something else. Now the conductivity is 124. And finally, when we get down near the mouth, the conductivity is risen to 319. And that was not taken from the main creek. That was taken from a side creek. And someplace up on this mountain up here, there is an old mine. And I don't know what it has for tailings, but this is picking up some mineralization probably. And then the creek mouth is where we started with our water analysis and where I finish with this talk.
Well, that's that's great, Richard. There's a few really good questions on here, which you're probably gonna have to go back to the beginning. But there's a couple of them, and maybe just answer them together. Like Alison Lutz says, what level of conductivity reading would you find concerning? And then Ali Ferguson, how is conductivity affected by surrounding geology? So maybe those two, maybe you could go back to that Silverton map and just sort of address those. What do you think?
Yep. The first one, Alison's question was, when do I start to get concerned?
Yeah.
The answer is basically shown on this slide here. Up until a conductivity of about 300, I'm pretty happy with my correlation. and it's telling me that I'm dealing with normal sodium bicarbonate waters here. When I start seeing higher numbers than that, I probably am dealing with something that's got some limestone nearby, and it doesn't necessarily mean that it's bad. It's when it doesn't fall on that straight line. This one here is from I think that one is that one is a sulfate water. That one is picking up some that's some Bonanza Marsh up here, and I think it's a spring that's coming into the system, and it's coming through because of the high sulfate content. It's coming through an anhydrite or gypsum bed within the limestone. There's a limestone area there. This one over here, it is down at Foamy's Bakery, north of Winlaw, and it's picked up a whole bunch of sodium and a whole bunch of chloride, and our interpretation is it's probably picked up road salt somehow into that sample. It's just off of the sample was taken just off of the rail trail below Foamy's, so it's not directly connected to the highway, but it is just below the highway at Foamy's. So I get concerned when I start seeing different patterns, and so this is the reason why I like to have a whole bunch of water analysis over time, and that's what the Cabin protocol does on streams. Is if you actually take samples weekly, say, or after events, you can actually see this pattern, and you'll get the type of plot that I showed you earlier of those two streams showing the cycling, the yearly cycle, like that. So those are our weekly analyses, just using the specific conductivity. This one would concern me a great deal because of the high cycle amount to it. So it's not quite exactly answering. It's not a simple answer for Allison's question. The second question was, pardon me?
The second question was, how is conductivity affected by surrounding geology? Which I kind of thought you were talking about when you went over that map.
Yeah, that's. Let me run you through it, because when I talked about it, when we were doing our floating through the air and looking at the swamps and following the trail of the water, what we had, I'm going to get that pen back here if I can. There we go. This area down in here, all of this area here, is all granite. We started off on the top of this mountain up here, right above the tarn. We went down in through granite, but there's soil, and that's where the main part of it was most of the ions were coming from. Down through the wetland here, came to the junction. Now when we turned and went to the west, or west-northwest here, the stuff on this side was all granite. The stuff on this side was all the metamorphics, and these metamorphics have the mineralization in them. This is Idaho Peak up here, and down in here is all the mineralization that has been mined for years since the turn of the century, and it's all lead and zinc. So the geology is telling me that I can expect different types of water. This when I'm going through metamorphic rocks. This is a combination of igneous granite and metamorphics on that side. I hope that answers Allison's or the other question.
I think so. We've got one more, and this one is a toughie, and I was actually thinking of just seeing if I could unmute Susan. But she says, her 12-month conductivity at Mather Creek ranges from 85.4 to 219.4. And she says, what does that tell you? Or what would, I guess that's her question.
Okay. Okay, and the question, the I would need more information to determine what is happening on it, to see how big the watershed is. If it's a small watershed and there's a bit of mineralization, as I showed you on this previous one here. Let me get back to here. This one has an unbelievable cycle to it, but this is a short and small watershed, so it's highly affected by the mineralization there. This one, on the other hand, is a fairly long, runs through the middle of Red Mountain, and it's a fairly long and wide watershed, and takes in a fair amount of area. And you'll see that it varies from about 95 to 140. What were the numbers she had?
I'm going to unmute
Susan?
her and see if that works. Okay, Susan, you're going to be able to speak to Richard. Hi, Susan.
Hey, this is Susan.
Hi, Susan.
Can you hear me, Richard?
Yes,
Yeah.
I can hear you fine. Thanks. Good to hear from you.
So it's I don't know, relatively, the watershed is relatively big for a small stream, I suppose. And it flows through the Purcells north of Kimberley. So, and I got someone looking at the geology for me, but I couldn't say whether it's all mostly igneous or mostly metamorphic rock. There's been a fair amount of logging up near the top of the watershed. There's a fair amount of human use through the middle and lower reaches of the watershed. I don't know if that helps you any, but I've looked at the cycle, and my numbers definitely follow the cycle, the pattern that you described. That is, the conductivity falls with the greater flow and increases with decreased flow. I mean, my numbers match that. And you did say that numbers up to 300, you would think we're okay or even good. I'm not sure. So my numbers are all well below 300. So I'm thinking that's probably a good sign.
I'm guessing that it's a normal calcium bicarbonate water, that it's reacting the same as this one that is showing on the screen. And you're probably mostly metamorphics there. The example that I was using earlier was unique in that it's sitting on the edge of the Nelson batholith, which is a massive granite intrusion. But over in the Purcells, I think they're mostly sedimentary and metamorphics over there. I could be wrong because I don't have the map in front of me. But no, I think you've got a relatively normal cycle happening there. And so now you can concentrate on is your logging or disturbances, are they causing any increase in the metals? So you're going to need full analyses for those.
So should we be measuring, doing an analysis from the top of the watershed down to the bottom? Our monitoring site is very close to where the creek empties into the Kootenay River.
No, I would continue to use the right down near the bottom because it's telling you the history and what's happening all up above. So I would continue using that same site because then you're getting consistent data. You don't need to measure all of those other points along the way unless you're trying to backtrack and find out where the high concentrations are coming from. But it doesn't sound abnormal to me at all here. I've got one creek here that runs under 100 most of the time, and I've got several that are running a couple hundred, 200, 300. So I wouldn't be worrying about that unless there is some unique heavy metal that's potentially causing a health concern.
Thank you, Richard.
You're welcome, Susan.
And thank you, Susan. I'm gonna mute you again now, just for the bandwidth. Excuse me. I think that, as far as I can tell, we've answered the questions that we have. As Richard said, you can send us a few more questions afterwards, and we'll, if we need to, we'll do a second session on this topic, or figure out some other way to answer your questions. So I would hope we could all. It's sort of funny not being able to hear you guys. I would like to thank Richard on behalf of everyone, and I think that's about it for today. Let me just.
Okay, I would welcome any.
Let me do a last-minute check for things. They don't always come in straight here. Yeah. No. Okay. So
okay,
thanks.
Well, I would welcome. Go ahead, Tara.
Oh no, go ahead. You had your email up on your last slide before.
Oh, yes. Yep. Let me get back there. Yeah, you can phone me or email me, and you can, if you want a copy of these this presentation, I'd be happy to send it to anybody that emails me, and I will also file one with Tara so that she can send it out in case you want to get in touch with her or have lost my numbers. And thank you all very much. You've been a very attentive audience as far as I can tell, because I can't hear you, so it must be working.
Okay, thanks, Richard, and thanks to everyone. We're gonna close off now. Thanks very much.